Okay, more circuit components. So we'll talk about analog and digital circuits, mostly solid state type stuff, a little bit about displays, connectors, and more about ferrite cores. So what is an analog integrated circuit? Well, first, an integrated circuit is a usually is a silicon substrate that has a lot of devices on it. In the case of an analog integrated circuit, they're going to be analog type devices. Things like voltage regulators, um, some sort of filters where it's made up of inductors and capacitors, resistors, uh, just different types of analog devices on a single substrate. Whereas when we talk about a digital, uh, it's a similar substrate, but it's got uh, usually logic gates on it with typically no analog circuits, although you could have hybrids. So most of the time, either it's going to be voltage regulators or operational amplifiers, uh, be the most common. Wideband RF amplifiers, like when a little bit we'll talk about MMICs, would fall in that category. Some of the filters I mentioned. The main one to remember is operational amplifiers. And that's a special type of amplifier, which we don't go into much on the general, but you learn a lot on the extra about operational amplifiers. So a digital integrated circuit, like I said, is just logic gates on a single piece of uh, semiconductor material, typically silicon. Some of the very high speed stuff might be on other material like gallium arsenide, things like that. Uh, we kind of have two different types of logic gates, families, I should say. The transistor logic, which has been around uh, since I started in engineering, and it's still out there. It's called transistor logic. Uh, it has relatively high speed, but it also has high power consumption. At some point, they came up with CMOS, which stands for complementary metal oxide semiconductors. And those were purposely designed to operate at lower power levels. So they have a much lower power consumption than an equivalent TTL device. So uh, it's an AND gate or an OR gate or a flip flop. It will have lower power consumption, probably not quite as high as speed, but they've gotten a lot better with the CMOS as the TTL families. And there's variations in the TTL. They came out with low power TTL and Schottky TTL and high power TTL, which is even higher power. Um, and similar things in the case of CMOS, and there's a bi-CMOS, which is a hybrid between the two. You don't have to remember that one. Just the high power and low power. Um, some of the digital circuits are memory integrated circuits. So there's uh, essentially millions of flip-flops to implement the random access memory or a ROM memory, which is read-only memory. It's non-volatile. Uh, the two types of memory are, as I mentioned, RAM or random access. Uh, it's called volatile because when you take power away, it essentially uh, loses all of its data. Everything goes back to the default state. In the case of a ROM or read-only memory, um, it's not programmable, so the memory is fixed. So it doesn't require constant power. If you take the power away and you bring the power back, it still has the same contents because they're physically implemented ones and zeros at those memory locations. I mentioned monolithic microwave integrated circuits, which is another of the uh, analog type devices. These are kind of special purpose amplifiers intended for RF applications. Um, they they actually operate below 300 megahertz, but they go up into the 300 gigahertz range. I know that because the power amplifier in um, the device I'm building is below that, and it uses MMICs. Um, like I said, they're specifically targeted to RF amplifier applications, and they're built with a 50 ohm input and output impedance. So it's very easy to connect them together to other devices with 50 ohm transmission lines, which you can actually implement on a circuit board instead of actually a coaxial cable. And it's called microstrip or microline. And you can build them such that with the right width and spacing, they have a 50 ohm characteristic impedance. Uh, display devices, very popular today, are light emitting diodes. You see them in almost everything. Uh, and they're used to convey information. Something's on or off. We can use the colors. There's RGB type where they have 3 pins and you can control the color of it to indicate, give you different information. Like for a temperature indicator, you might be green and then start turning yellow or red as the temperature goes up. Um, it's still a diode. It's a p-n junction. It's typically made with other material than silicon. So the forward voltage for it to conduct is normally a much higher voltage, up in the 2, 3, 4 volt range, because of the materials they use. And that's because these different materials emit different color light or enhance some of the light that's emitted. Now, you don't need to know this, but it turns out that a p-n junction, whether it's a transistor or a diode, when it's conducting, actually emits photons or light. So they discovered that characteristic, and that's how they developed the light emitting diode by putting it in a transparent in uh, encasement so it would let the light out. Um, so in need to remember that they emit light when they are forward biased. So whenever your voltage is above the threshold voltage for that particular light emitting diode. So like I said, they're typically not silicon, so it will be some higher voltage. The other class is liquid crystal displays. These tend to be extremely low power. You will see these in applications. I don't know that I've seen any around here, but there's an application where people have actually implemented price signs on food and grocery stores using liquid crystal displays and some very low power uh, processing devices so that they can, uh, over RF, actually update the prices on all the products. I don't know if it's still, people are still doing it, but it was available for a while. The one thing that you need for the liquid crystal display is you have to have some form of light in order to be able to see it. They do not emit light. They actually block light. So you have to have a backlight between it, or it has to be a clear substance where light is coming in from behind, or you're looking through it. And you don't see that type much anymore. Most of them have a backlight. So most of the devices you see on radios and things today are actually liquid crystal displays with some form of backlighting, and they've developed where they're color, not just black and white or off and on like they started off. And it's actually uh, a crystal that's kind of a liquid form, and it allows the actual crystals to either be random or align when you apply a voltage between sort of the plates of the display. And those are made with a conducting material so you don't see them. So when you apply the voltage, you can align the crystals so they block the light. And what you see are dark letters uh, in the simple ones. A little more complicated for color. We also use connectors. You need to get familiar with connectors. It's kind of defined as an electromechanical device creating an electrical connection between parts of an electrical circuit or between circuits, joining them into a larger circuit. Most of the time, we give them a gender, and we say the male is called a plug, and the female is called a socket. They may be removable, like on coaxial connectors, uh, things like that. A lot of times they require tools, and in the case of um, like your power crimp type connectors that you'll find a lot, those require a crimping tool. Uh, I guess I said when on coaxial cable by removable means you can unscrew the connector from whatever it's connected to, but you don't remove it from the cable because you need special tools to put a coaxial connector on a coaxial cable. At least, well, at least as a minimum, you need a soldering iron and an X-Acto knife. It's a whole lot easier with some other tools. So we have different types, and they're classified by frequency. So in the audio frequency, what you're going to find mostly used are called RCA phono plugs. You're probably familiar with those. Uh, they used to, do the audio into the back of your TV to your stereo. Have um, a red and a white and a yellow usually, and they're joined in a 2 or 3 conductor cable. When we get into the VHF range, where we're talking the 30 to 300 megahertz, where uh, most amateur radio operates, you're going to find PL259 connectors are mostly used, and they're good for most of that range. Really not too great at 300 megahertz, but they're fairly cheap compared to some of the others. When we get up to the UHF range, in the 300 to 300 gigahertz range, well, actually, that's a lot longer than UHF, but um, you'll find most test equipment that operates in the RF range will either have BNC connectors or type N connectors on it. BNC is probably the most popular, and they're good up to about 4 gigahertz. The N-type connector, which most amateurs tend to use when they're doing UHF, like 70 centimeters and 23 centimeters, and they're good up to 10 gigahertz. They're also a little more waterproof than the other connectors, the way they mate. So you don't have to worry as much about waterproofing them with tape. There's also a third type called an SMA. They're about a 1/4 inch in diameter. They're threaded. They're a pain sometimes because unless they're perfectly aligned, they won't start threading on. So when you're working in tight spaces, it's very hard to get it positioned right to get it started. But they're good up to close to 18 gigahertz. And you'll find these a lot of times inside of high frequency or VHF radio equipment to connect modules together. Here's an assortment. These are not all to scale. Like I said, these SMAs are only about a 1/4 inch. The N-type connector is about 3/4 inch in diameter. I have never physically seen the TNC, but it looks like it's some variation of the N-type, and it means it probably costs even more. This SMC and SMB are variations of the SMA, not very common. The MCX connectors I've seen inside of laptops where they connect your network card to the antenna. And they're little snap-on connectors. They're very, very small. That's probably a 1/16 of an inch in diameter. The BNC, which actually stands for British Naval Connector. Like I said, they're very common on test equipment. You'll see it on QRP type equipment a lot. They're very handy because it's a quick disconnect. You push it on and twist and it locks in place. You don't have to try to get it lined up and screw it on. And last but not least is the PL259, which they label as a UHF. This again is about the same size as the N connector. Turns out it's actually the same thread. I found that at the ham show looking for a cap for N connectors and wondered why they only had one type, and it turned out to be because it's the same thread for both. Um, like I said, they claim good to 300 megahertz. I'm a little doubtful on that. Um, we also use, I mentioned the ferrite cores a lot for doing inductors for like bandpass filters and low pass filters because we can get very high inductance with a low number of turns. Um, the frequency range will be determined by the type of material or what we call the mix. Some of the standard mixes are classed as 77, 75, 3, 52, 40, 31 is the most popular mix. It covers basically the HF range. So it's very good for that. These others tend to cover ranges of higher frequency but narrower bandwidth. So they can be used for kind of more special purposes. You can find that material in rods or beads as well as toroids. And they also can be used to create a high impedance, essentially an inductor that you put around a coaxial cable to reduce the common mode current on the outside of the shield of that cable, if there is any.
So, Robert, if you were starting up your shack, you would go ahead and get some 31 ferrites just to have just as your supply, or what
Well,
would you get to
well,
mix them?
if I was intending to wind toroids for something like that, yes, probably.
Okay.
But they're fairly cheap. There's some sites like Kits and Parts. He's called the Toroid guy, and he has most of the mixes and sizes and stuff. Um, they're they're not too expensive. This is
Okay.
a chart showing some of the characteristics of the different mixes, and you can see 31. Um, depending on what you're going to use it for common mode suppression, it's really good for the entire HF band up into part of the VHF. If you're using it for a wideband transformer, it's good in that same range. They tend to be lossy, so they're not normally used as a tuned circuit. Some of the others, like the 43s and 52s, 61s, you'll see they can be used as tuned circuits in those ranges. Um, really, these 73 and 75 Js are kind of special purpose. The one thing you notice is a permeability number, and that's essentially a measure of how much inductance you can get per turn. So you can see the 75 is going to give you a lot more inductance with fewer turns than the 61 is going to give you. You don't have to remember any of these numbers. It's just so you get an idea of what they do. We talked about common mode current. And we'll use this example of a half-wave dipole. And in most cases, the half-wave dipole isn't perfect. Both of these legs are supposed to be a quarter wavelength long. Well, if they're not exactly a quarter wavelength long, you're going to have the different current balance on one side than you are on the other. Well, you say, why does that matter? Well, if you're feeding this with a coax, the current that's flowing through the center conductor of the coax is essentially forced by the charges to be equal and opposite on the shield. But you notice that that current is traveling on the inside of the shield of the coax. So in reality, a coaxial cable, which has a center conductor and a shield, has three conductors. It has the center conductor, it has the inside of the shield, and it has the outside of the shield. There's one thing to remember is RF. I don't know if we've talked about it in any of these. RF current tends to travel on the surface of a conductor. The higher the frequency, the closer it is to the surface, or the least amount of depth it has in the conductor. So if I1 and I2 are equal, but I1 and I2 are not equal up here, then that excess current has to travel on the outside of the conductor. We call that common mode. So that current's going to travel all the way back to your shack. Now, it may not be much, but it could be a lot. You can also pick up extraneous signals on the outside of the conductor. Remember, it looks like a wire on the outside. So that can also look like additional common mode current. So you want to try to block that by putting usually a ferrite bead, or running the coax through a few turns on a toroid core, or what they used to do and still do in some cases before they had the toroid cores is up close to the antenna, they would wind the coax in 4 or 5 loops to make a coil to create that inductance on the outside to impede the common mode current. Does anybody understand that?
Not really. Be honest with you, not really.
Well, we'll see. The questions
Basically,
aren't.
yeah, basically you're just saying you have three channels on your common mode as long as everything is equal, but there's the current itself, and then the inside and the outside of the coax, and it can travel backwards on the outside of the coax, correct?
Correct.
And then to
Because
eliminate
remember,
that,
the inside currents, this I1 and I2, have to be
mhm,
equal.
mhm,
So
right,
whether it's an antenna or something else they're connected to, if the currents aren't equal for whatever reason, and it can
gotta
be a
go.
lot, that excess current has to travel on the outside of the shield. So the whole point of we call these common mode chokes. The whole purpose of putting it there is to reduce the common mode current.
Gotcha.
Okay, so what did we learn? basically analog and digital circuits. In the analog, we need to remember that the typical type are operational amplifiers. Those are analog devices, and there may be more than one amplifier on the single substrate in this integrated circuit. In the case of digital, they're normally going to be some form of TTL logic or some form of CMOS for lower power. It's possible to have both, but essentially they're all digital devices, either TTL or some form of CMOS. Another type of integrated circuit are the microwave ICs, which are specifically built as normally RF amplifiers. So that's why they have the 50 ohm input and output impedances. And a lot of times it's a fixed gain amplifier. All you do is make connections to the input and output, apply power, and you got a 10 dB amplifier that works in the gigahertz range. So they're very simple to use. The display devices, we talked about several, but essentially the LEDs only emit light when they are forward biased. So whatever that forward threshold voltage is, whenever you overcome that, they start to emit light. In the connectors, we talked about BNCs being good to 4 gigahertz. Important to remember that number. N-type connectors were moisture resistant, useful to 10 gigahertz, another important number. The SMAs, small threaded, useful to 18. I think they may say several on the test question. I'm not sure why they said that, but we find the RCA phono connectors are the most commonly used for audio or some low voltage DC circuits. A lot of times you will have a connection between your transceiver and a power amplifier for the ALC or automatic level control between the two. So you can control the power amplifier that way. And most of them I've seen that tends to be an RCA phono connector. The ferrite cores, mostly you're going to see toroids. You may see some rods. They have different mixes that determine the frequency and they say impedance, inductance characteristics. In other words, what that permeability value was. You can get very large values of inductance depending on the permeability, which is a function of the mix. The magnetic field, like we said before, is almost totally contained within the core. You use them as common mode choke to create a high impedance on the outside of the shield of a coax cable. So, what kind of device is an integrated circuit operational amplifier?
Oh no.
Delta.
Delta.
Delta. Which of the following is an advantage of CMOS integrated circuits compared to TTL integrated circuits?
Alpha. Low power for Siemens.
Yes.
Somebody's got a hum. We have a ground loop somewhere.
We do.
What is meant by the term MMIC?
Monolithic. So bravo.
Bravo, yeah.
How is an LED biased when emitting light?
Going forward. So delta.
What's a typical upper frequency limit for low SWR operation of a 50 ohm BNC connector?
Yeah, Charlie.
Charlie, which of the following describes a type N connector?
Alpha.
Alpha.
Very good. There's a better
Moisture.
picture of one. And part of the reason it's moisture resistant is this little internal shell that slides inside of a mating tube on the other end. So it kind of seals it up pretty well. Whereas on the PL250, the PL259 connector, you don't have that. So you just have the center conductor and this outer shield, which doesn't make it watertight.
I'm gonna turn my audio off and tell me if that interference clears.
Yes?
I still had it off. Did it stay clear the whole time?
Oh, I think so. It came back. It's gone now.
Wow, so it's between you guys.
Must be me. Don't know what it is though. Okay, sorry. Go ahead.
All right. What is an SMA connector?
Bravo.
Bravo, because of several gigahertz.
And I don't remember what SMA stands for, but you don't need to know it anyway. And there's a better picture of the SMA. So there's nothing to help align it except for the threads, so tends to be difficult in tight places. Which of these connector types is commonly used for low frequency or DC signal connections to a transceiver?
Charlie.
Charlie.
Yep, good old RCA phono connectors. What's an advantage of using a ferrite core toroidal inductor?
Delta.
Well, I was gonna say it could be delta. Yeah, delta.
Very good. How does a ferrite bead or core reduce common mode RF current on the shield of a coaxial cable?
It's the impedance and the current. So it's got to be alpha.
I was gonna say bravo. Maybe I'm wrong.
Well, you are.
How do you reduce it? So your question is yeah, it converts it, I thought. On the outside. Makes it a common mode current. Or am I reading that
No,
wrong?
it's already a common mode current. What you want to do is block it. That's
Oh,
why
okay. So
that's
then
why
it
you
has
create the impedance on the outside of the shield. By putting that
I didn't catch
toroid outside, it has no effect on the center conductor or the inside of the shield. It only affects the outside of the shield.
Got it.
What determines the performance of a ferrite core at different frequencies?
Is it Charlie?
Charlie.
Is Charlie. Those were
That
easy.
wasn't too bad.
No, you guys did pretty good. Remember, you can miss 9.
Mm-hmm. Yeah, I don't know what this interference is because I didn't have it. It just all of a sudden started. So something's changed. I don't know what.